Hi, this is the first video for the probability. Both Year 1 and Year 2 probability have been bunched together to make one topic. So some of the exercises that are referenced in these videos will be from Year 1 and some will be from Year 2. So you need to look out for that and use the correct active learn book when you're doing your exercises. These are the objectives that we're going to do throughout the series of videos. So we need to calculate probabilities of simple events. We're going to look at the use of Venn diagrams. We're going to use union and intercept notation and how to work out which parts of a Venn diagram we need. We're going to look at conditional probabilities. We're going to look at the concepts of independent and mutually exclusive events. And we're going to use tree diagrams throughout for different questions. In this first video, the first video should just be a review really of what you know from GCSE. So here is a load of terminology or vocabulary that you are going to have to understand as I explain these slides. So if I say something about a trial, the trial is any repeatable process. So the thing that you are actually doing, like throwing a dice or tossing a coin, spinning a spinner, that's the trial. The outcome from that is the result from that experiment. So it might be throwing a 5 on a dice or getting a head from a coin. The event is the set of outcomes in which we're interested in. So there's the example, getting an even number from a dice or getting a red from a spinner, whatever it happens to be. That's the event. And a sample space, well, that's a list or a table of all the possible outcomes. It could just be a simple list. If there's two things happening at the same time, you could do a sample space diagram showing all probabilities on a Venn diagram. That's a sample space. So it's anywhere where all possible outcomes are shown. We use capital letters to denote events. So it's unlikely that you'll get lots of words to write in terms of descriptions. Sometimes there'll be a context. Other times it will just say probability of A equals probability of B equals, and there'll be no context. So we use capital letters to represent the event. So A might be the probability of getting an ace. So we would write that as P bracket big A. And that's the probability that A occurs, the probability of getting an ace. A little dash, that denotes the probability that A doesn't occur. Okay, so you need to know all of those words and what their meanings are. There are different ways in which we can calculate probabilities, and all of these will be used throughout. You don't necessarily need to say what they are, but it's good for you to understand what the differences are. Theoretical probabilities, well, these are based on what we call equally likely outcomes. So they're based on equally likely outcomes. So an example of that would be rolling a dice. So if you roll a dice, all the numbers 1 to 6 are the outcomes, and then they are equally likely to happen. Tossing a coin, head and tail are the outcomes, they are equally likely to happen. So it's something that we can physically calculate based on the outcomes that we know about, how many there are, and that they are equally likely. Experimental probability, well, it says what it is. It's based on an experiment, so based on trials in an experiment or using previous information. So you could, for example, For example, if you wanted to know whether toast falls butter side down, what's the probability of a piece of toast falling on the floor butter side down if you dropped it? That's not something that you could work out theoretical probabilities for, but you could work out the probability by doing an experiment. So you might, for example, drop a piece of toast onto the ground from a 2-metre height repeatedly and count how many times it lands butter side down. The more times you do it, the better the estimate of the probability. We use experimental probability for making odds, for example, horse racing. The odds on a horse race are dependent on information, so things like the age of the horse, whether it's raining on that day, how good the horse has been on wet or firm ground, how many of the last 8 races, for example, the horse has won, the age of the horse, the weight of the jockey. So loads of different information is gathered for then a probability of it winning to be given. So that's experimental probability. So either a physical experiment or using previous information. Subjective is just a matter of opinion, really. Okay, so for example, I think the probability that my cat will bring in a mouse today is about 0.9. Okay, no particular evidence, just apart from the fact that he likes to bring in mice a lot. Okay, so it's subject, it's matter of opinion. So those are the 3 different types. How to calculate a theoretical probability? Well, you know this already. Where outcomes are equally likely, the probability of an event is the number of outcomes in the event divided by the total number of outcomes. And we call the ones that we want to get the favourable outcomes. So, for example, if you want the probability of getting a number less than 3 from a dice, well, the favourable outcomes will be the 1 and the 2. And the total number of outcomes will be 6. So the probability of getting a number less than 3 on a dice is 2 out of 6. So the ones that we want are the favourable outcomes, and then it's out of how many outcomes there are. Impossibility, for something to be impossible to happen, that's got a probability of 0. For certainty, that's got a probability of 1. So all probabilities range from 0 to 1. So you're going to be writing probabilities as either fractions or decimals, sometimes percentages, but it's usually easier if you work with fractions or decimals, never as a ratio. The probability that something doesn't happen, well, that's 1 minus the probability that it does happen. Okay, so those are theoretical probabilities, but you know all of that already. This is a reminder in ways in which you can show outcomes. So we could list, so we could physically just list all the different possible outcomes. We could do a sample space diagram. So that's usually a 2-way diagram for 2 things that are happening at the same time. We could show on a Venn diagram, or we could show on a tree diagram. Now, in the questions, you may be asked to draw one of these specifically. So it might say, show your probabilities on a Venn diagram, or draw a tree diagram. Other times, they'll just ask you a question, and it'll be up to you to choose what is the most appropriate thing to draw. Okay, sometimes there might be a 2-way table as well. That's often used as well. Okay, so it's quite often up to you to use what the most appropriate and most efficient way of drawing it in order to work out your probabilities. So I'm just going to do 3 little questions. These are similar to the ones that you will have done at school. So 3 fair coins are tossed. what is the probability of getting 3 heads, exactly 1 tail, at least 1 head? So ways in which we could show the outcomes, we could draw a tree diagram, though that would be quite a busy tree diagram. I would probably just list it and try and list the outcomes systematically. So you could get 3 heads, or you could get 3 tails. You could get the first 2 could be heads and the third could be a tail, or the first 2 could be tails and the third could be a head. Or you could get a tail and then 2 heads, or you could get a head and then 2 tails, or you could get a head, then a tail and then a head, or tail, head and tail. And there are, as you can see, 8 different possible outcomes. The order in which you get them does matter. So even though these have 2 heads and a tail, each outcome is different due to the order in which you got the heads and the tails. So they count. So you've got 8 different outcomes in total. So it was a nice one just to list all the outcomes easily. The first one, question 1, the probability of 3 heads. Well, that's just 1. There's 1 favourable outcome out of 8. Question 2, exactly 1. So 3. So there's 3 favourable outcomes out of 8. And then at least 1 head. Well, either you can count all the ones where there's at least 1, there's 7 of them, or you can do 1 minus not getting any. Okay, but either way, that's going to be 7/8. Okay, we'll look at the next question. So I'll just move it down. 2 spinners are numbered 1 to 4. They're spun and their product is calculated. Find the probability of the product being an even number or more than 8. So for each of these, we need to see what the outcomes are. In order to do that, as there are 2 things happening at the same time, rather than a list for which there are going to be quite a few different possible outcomes, what we could do is draw a sample space diagram, and this is just a grid. You'll have seen these in school, I'm sure. We've got spinner 1, spinner 2. So in the top row are all the outcomes from spinner 1. And then in the column, the first column, are all the outcomes from spinner 2. So each spinner is numbered from 1 to 4. And then we've got to find the probability of the product being those. So we're going to have to times them together. So inside here are going to be the products. So if we fill that in by multiplying the numbers together, so all the blue numbers, you can see there are 16 outcomes, and by drawing them on the table, we can see what they are. Now we want the probability of it being an even number. Well, there's 1, 2, 3, 4 odd numbers and the rest are even, which means there must be 12/16 or 3/4. The probability of getting more than 8, so that doesn't include 8. So you can just see that there are those 4 values. So there's the probability of getting a number greater than 8 is 4/16 or 1/4. Okay, so if there's 2 things happening at the same time and you need to see lots of outcomes, it's worth just drawing a quick sample space diagram. And then the other thing that you might see, you may not have seen these at school. I'm really sure you've seen a table, but you might not have done probabilities on them. We've got a grouped frequency table. So it's all about time, the time taken in minutes for a group of students to complete a number puzzle. So we've got times from 5 up to 15 minutes, and then the frequencies. A student is chosen at random. Find the probability that they finished the number puzzle in under 9 minutes. So we want to know how many students did the puzzle in under 9 minutes. Well, that's these here. So those 19 students did the puzzle in under 9 minutes. But what's that out of? Well, it's out of the total number of students. The total number of students is all of those numbers added up, and that's 40. The next one, a student is chosen at random. Find the probability that they finish the number puzzle in over 10.5 minutes. So this one's a bit trickier because 10.5 is in there. So in order to do this, we need to, first of all, make an assumption. And the assumption is that these are evenly distributed about this group. Okay, so actually the probability that we are going to work out for this one is just going to be an estimate based on that assumption. 10.5, if you think of this is a group size 2. So if we split that into 4, it's going to go from 9 to 9.5. It's going to go from 9.5 to 10. It's going to go from 10 to 10.5, and then from 10.5 up to 11. So if we split it in 4, this is the one. 1/4 of those took longer than 10.5 minutes. So what we're going to do is we're going to take 1/4 of those. So 1/4 of those is 3, plus the 5, plus the 4, over 40. So that's 12/40ths, or 3/10. Okay, so if you've got to go within a group, you need to split that, assume that these are evenly distributed across the group, and then split the group up into however many parts you need. Okay, so that's just a reminder. There are some questions similar to that from Year 1, the Year 1 textbook, exercise 5A. So if you feel you need to, have a go at those. The other thing I'm going to do on this video is just to do a review of tree diagrams. So you will have used tree diagrams at school again. These can be used to show multiple events happening one after the other. So it could be 2, 3, 4 sometimes happening more than once. So twice, 3 times. Okay, and it can be for both independent and dependent events. So you will have done questions where you're replacing something or where you're not replacing something. Doesn't matter, the way we work out probabilities from a tree diagram is the same. So we're just going to look at 2 examples. The second one's a bit more complicated in terms of drawing the tree diagram. So first one, Dave likes to vary his breakfast choice. He likes cereal or toast, and to drink he likes coffee or juice. The probability that he chooses cereal is 0.4. If he chooses cereal in the morning, then the probability he chooses coffee is 0.7. If he chooses toast, the probability that he chooses juice is 0.9. Illustrate this on a tree diagram. Okay, so we have got his drink's choice is dependent on his food choice. So first, we're going to put the food choice. So the first set of branches is going to be for cereal or toast. And it says, what does it say? The probability he chooses cereal is 0.4. So the probability he chooses cereal is 0.4, which means the probability he chooses toast is 0.6. These are what we call exhaustive. They're the only options, so together they must add up to 1. He's only going to choose cereal or toast, nothing else. Okay, so then the drinks are dependent on his food choice. So he can either choose coffee or juice, coffee or juice. If he chooses cereal in the morning, then the probability he chooses coffee is 0.7, which means that must be 0.3. If he chooses toast, the probability he chooses juice is 0.9. So that's 0.9, which means that must be 0.1. So that's your tree diagram. So remember, each of these has got to add up to 1. Find the probability that he chooses cereal and juice. So the probability he's going to choose cereal and juice, what we do when we use a tree diagram is we multiply along the branches. So cereal is 0.4 times by juice, which is 0.3. So 0.4 times by 0.3 is 0.12. Find the probability he chooses coffee. Well, he could choose cereal and then choose coffee, or he could choose toast and then choose coffee. So cereal and coffee, toast and coffee. And then we've got different options, so to get it combined, we add the two things together. So we've got 0.28 plus 0.06, which is 0.34. Okay, so we times along the branches, and then if there's multiple ones, we add them up. Okay, a game at a fair requires the player to hit a red target with a ball from 4 meters away. The player can have 3 attempts and can move forward 1 meter after each attempt. Results from the study show that the probability of hitting the target on the first attempt is 0.1, on the second 0.3, and on the third 0.6. When the target is hit, the game is over. So on the first attempt it's 0.1, on the second attempt it's 0.3, and on the third attempt it's 0.6. And when it's hit, it's game over. Now that's important because that means that actually some of the tree diagram we're not going to need. So what we don't want to do is overdraw. Illustrate on a tree diagram. Okay, so first attempt, we can hit the target or we can miss the target. I'm just going to put an M. I could put H dash for not hit. The probability of hitting on the first attempt is 0.1, which means that must be 0.9. Now, if we hit on the first attempt, that's game over. So there's nothing that needs to follow this particular branch. The only time we're going to need a second attempt is if we miss the first one. So here, given that we miss the first one, we can then hit or miss on the second attempt. So that's going to be 0.3, which means that's going to be 0.7. And then the same again, if we hit the target on the second attempt, that's then game over. So no extra branches here. If we miss the target on the second attempt, then we can have another attempt, and that's 0.6, which means that's 0.4. If we hit the target here, it's game over. If we miss 3 times, game over, because we've got 3 goes. Okay, so that's what we need in terms of the tree diagram. Now we can use that to work out our probabilities. So calculate the probability of losing. Well, that just means that we miss the target all 3 times. So the probability of losing is going to be 0.9 times 0.7 times 0.4, which is 0.252. I hope. Okay, calculate the probability of winning on the second attempt. Well, the probability of winning on the second attempt means that we must have missed on the first attempt. So missed and then hit the target. So that's 0.9 times 0.3, which is 0.27. Calculate the probability of winning. Well, either we can hit it on the first attempt, or we can get it on the second attempt, which we've just worked out, or we can get it on the third attempt, which is 0.9 times 0.7 times 0.6. That comes to 0.748. There is a quicker way of doing it. The probability of winning, that's going to be 1 minus the probability of losing, which we did for part A. So it doesn't matter how you do it. This was slightly more efficient, but it'll give you the same answer if you do it the long way around. Okay, so the point of that tree diagram was sometimes you won't need to have all the branches. So don't just start drawing loads and loads of branches that you don't need. That potentially would have been quite a big tree diagram had we had extra branches on. So really read the wording carefully. Make sure you only draw the branches that you need. Okay, so you should be okay with tree diagrams from school. We will revisit them again later on in a different video. Tree diagram practice, exercise 5D. This is also from the Year 1 textbook. Miss out question 4 because it's got something in there that I've not done yet. Okay, that's the end of the first video. On the next video, we're going to look at Venn diagrams.